So I want to go over this, and I want to do it a little slowly today to make sure that, that I go at a pace that everybody understands. So we discussed stacks, which again, this is like the levels of understanding. Most of you are probably familiar with a stack. Maybe a few more of you have actually seen the stack-based, like the parentheses thing. But one of the most fundamental uses of a stack is that you can convert any code that uses recursion to a non-recursive code that uses a stack. Okay? So I'm going to work through one example which is somewhat simpler, and then I'll do a more complicated example today, which is like the main focus of the lecture. Okay, so I have this function that I call print reverse that's going to print an array in reverse. That's what it does. Okay, so how does it work? Print reverse takes two indices, I and j, and it's going to print the portion in between I and j in reverse. Right? And the way it does that is it makes two recursive calls. So the way to think of what's happening here is that it's splitting the array in half. This part over here, the first half, is linked to that call. And the second half is linked to the first call. So in English, the logic is to print an array in reverse, break it into two parts, recursively print the second half in reverse, then print the first half in reverse. That's the logic. So note that I've flipped the order, right? So I print the right half first in reverse, then the left half. Which makes sense because I'm reversing the array. Okay, so this is a recursive piece of code that prints an array in reverse. And of course, the initial calls are just, the initial indices are 0 and length minus 1. Okay, is this clear? Any questions? I still see a few laptops out. Unless you have an accommodation, you should put the laptop away. Yeah? I'm sorry, say it again. Well, okay, so you don't have to break this in half to print. You can print in reverse by just looping. You can print it in reverse in many different ways. So this is not, you shouldn't think of this as like the right solution for printing an array in reverse. You mean the question is, how did I come up with this recursive way of doing it? Practice. Lots, years of practice. But no, again, like you'll see more examples that I'll do. And I think once you do about 4 or 5 of these examples, you'll start seeing the pattern in them. When you see these things for the first time, they look like, how on earth could someone come up with this? Do any of you play music? Some of you. So I don't know, those of you who play music, do you know that like the more you practice, then it starts making sense then, right? Initially, things just don't make any sense. Like you look at a piece of music and it just looks like a jumble of notes. And then you practice more and then you start seeing patterns. Like, oh, this is what they're doing there. And this is what they're doing there. So a lot of this is the same. Well, okay, maybe that wasn't a good example because there are only about 4 or 5 of you who play music. But it's I think a lot of practice with recursion helps, which is hard because usually the way that you're tuned to code is iteratively by loops. But if you do more examples of recursion, it should make sense. I'll give another example today, and hopefully that will help. Okay. So anyway, so far so good. So this, at least even if you don't know how I came up with it, hopefully this makes sense. All right. We went over this example. So I'm going to keep now that I have 2 document cameras. Keep the code here. And so I said we described last time. So there. I want to simulate this code on this input here. 0 going to 50, right? So 0, 1, 2, 3, 4. And the way that you would simulate this code on paper is by making this thing called a box trace, where you basically write out sort of the recursion tree. Okay, so what is the first call? It's I is equal to 0, j is equal to 5, right? I and j are the indices here, so initially it's 0 and 5. So that's the first call. Now this code makes two calls. So let's look at the first call, which is I plus j divided by 2 plus 1. So become I is equal to 3 and j is equal to 5 because j is the same. Whereas in the second call, I is the same and the second argument is changed. Yeah? Fair enough? So we make a recursive call here. So for I equals 3, j is equal to 5, which then makes two recursive calls itself. The first call that it makes, which is I equals 5, j equals 5, is a base case. And so in the base case, it's just going to print AI and return. So it's going to print 50 and then return. Then the second call is made, so on and so forth. Is this any questions about this picture here? Okay, because you should ask me at this point if this doesn't make sense. Because if this doesn't make sense, the next step will not make sense. If this makes sense, the next step still might not make sense. But at least you're halfway there. Yes?
Sorry, I'm a little confused, I'll admit, but I don't know how to ask to clarify what I'm confused about exactly.
Oh boy, this is like a meta level question, right? Like
the two different calls to print reverse inside.
Yes.
Reverse.
Yes.
The first one is what calls the 5, the I equals 5, j equals 5.
Yes.
Time, right?
Yes.
And then from there, the second one is going to do I equals 3, I equals j equals 4.
Yes.
Okay, actually, I think I got it. Yeah.
See?
Okay, yeah.
How many of you are still confused? Raise your hand. No, raise your hand. I mean, you should be fine. Okay. All right. Few of you. All right. Okay. That's okay. Okay. Good. Like you should all do it together. Otherwise, if one of you do it at each time, go ahead. You have a question? Yeah. Go ahead. Okay, good. So like think about what happens when you do recursion, right? So when there's a recursive call made, the first call has to complete before the second call runs. So this entire portion has to complete before this will be processed. And so similarly, this has to finish before this is processed, right? So while the tree gives you this sort of big picture, it's really, okay, this is good. So it goes left, then it goes up, then it goes to the right, then it goes left again, then it goes up, then it goes right, so on. So because it has to complete this call before it can work on the next call. Yes?
To make sure I understand, it's like the first call is like kind of like finished going to the last element, and the second call is continuing it to go to the next.
So think of this portion. All of these calls are to the right half. This call is the right half of the right half. This call is the left half of the right half, so on and so forth. There is a name for this traversal. Yeah, we'll get there. Yes, we'll get there. Right. Yeah.
If I is greater than j, is that just for error handling on the input?
Exactly. That's just for error handling on the input, right? Okay. Good. So we have this. Now I'm going to simulate this process using a stack. Suppose I don't want to use recursion. Or rather, I want to think of the traverse. Okay, let me write down maybe all of these. So I believe that when I is equal to 0, j is equal to 2, what is it going to be? It's going to be I is equal to 2 and j is equal to 2, right? Which is then going to return. And then what we have here is that I is equal to 0, j is equal to 1, which then makes two calls. J is equal to 1, I is equal to j equals 1, and I equals j equals 0. So am I doing this right? Yes. How many base case calls are there? How many base case calls are there? 6. Is that a coincidence? Like, why is it 6? Yeah? That's how many elements are there in the array. And every element in the array gets printed once, and there are 6 elements in the array, so there are 6 calls, 6 base case calls, right? So this is a tree with 6 leaves. Okay. So you have this picture here. Now, what I'm going to do is to show you how one can simulate the entire process using a stack. So, how does that work? So the way to think about it is, when we make this call, so let's just start at the root. There are two calls that need to be made, the left call and the right call, except the left call has to finish before the right call is processed. So I'm going to push the arguments onto the stack. So I is equal to 3, j is equal to 5. So think of these as blocks of arguments. So I'm pushing those two onto the stack. Now here's the process that I follow. I pop the top of the stack, and I push its recursive calls in. Okay? I push its recursive calls in. So I pop an I and j, then I have two recursive calls that are made, right? I push the latter call first, then the former call later, because it's last in, first out, right? So the top of the stack is always going to be the next call that needs to be made, right? So I is equal to 3, j is equal to 5 is going to get popped, and in its place, I'm going to push in its two children. So I push the right child first, I equals 3, j equals 5, then I push the left child. That's the stack now. Again, now I pop the top. Now that's a base case call, so I just process it, which is just printing. Then I move to the next call, I is equal to 3, j is equal to 4. I push its children in, right, in sort of reverse order, right? So the left child is pushed at the end, because I have to process the left child first. And so I is equal to 3, j is equal to 3, I is equal to 4, j is equal to 4. These are now base case calls. So this will get popped, I print, I pop, and then I basically just print. Then I go to I is equal to 0, j is equal to 2, and I will repeat this entire process again over here. Yes? Yeah, so think of it as this got popped, I pop this, and I push its children in. So every time I take the top of the stack, so the process simply is, once I initialize the stack with this, actually I could even initialize with I equals 0, j equals 5. Initialize with the root. Now the process is pop the top of the stack, push its children in. If it's a base case call, then you just pop. You pop and you just do whatever is there. What I'm actually doing here is I'm almost simulating what the operating system is doing under the hood. I'm sort of like showing that to you, but I don't want to think in terms of the systems aspects. I just want to think in terms of the data structure. Does this make sense? So what this means is actually any recursive code, using this idea, you could convert into a stack-based code. Yes?
Is there usually like a benefit to doing that? Because I feel like recursive might be conceptually easier like while you're working on it.
So yeah, no, that's a good question. So well, first is the more ways we can look at something, the better it is for us. So that's one. But the second thing is actually in terms of efficiency, often the stack-based code will be more efficient, because when you're doing recursion, the operating system has an overhead in terms of like creating it's basically, instead of it creating the call stack, you create the call stack. So if you have a recursive code that's making, let's say, I don't know, maybe like millions of recursive calls, you might be better off using a stack to do it. And so that's another reason. Also but I just want to emphasize okay, the next example might make it even more clear. Yes, someone else had their hand up. Yes?
For a recursive call, something simple like traversing the linked list, the stack is a good replacement for that, or don't bother?
Probably not, no, right? Although for reversing a linked list, a stack makes a lot of sense, because if you think about it, like actually, if you simply push everything onto the stack, and then you read the stack, then you reverse the linked list. And if you think a little bit about it, the recursive implementation is actually doing exactly that, where the stack is the call stack. So, yeah. No, so you shouldn't think about the processing of the children and the stack as two independent things. We're not doing these simultaneously. We're using this picture to figure out how to use the stack. Right? So the way to think about the stack is that instead of doing a recursion, I could completely implement it using a stack, right? But I would use this picture to sort of tell me what is it that I need to push onto the stack when I pop something. That makes sense? We're going to do a more complicated example of this. So, and then I think, well, it'll help. So we'll do another recursive algorithm. But before that, let me first answer any questions you have about this. Okay, so far so good? Kind of, sort of, yes. You pop a base case you printed. Because again, if you think about the code, when you're in a base case, then you would just print and return. So there are no calls that need to be made before you return. All right. So let me do a somewhat more involved example. Okay, so I'm going to take this away. But 2 document cameras is nice, right? You can actually put code on one and analyze the other. Yeah. Okay. All right. So I will consider another. Let me start here. No, I should start left to right. So, okay. What should we do? All right. Okay, let's do this. Print all substrings. Okay, so printing all substrings. So what is a substring? So suppose you have a string A, B, C, D. A substring is a subset of characters in the same order. Subset, not necessarily contiguous. What I mean is AC is a substring, AD is a substring, BC is a substring. It's also contiguous. CA is not a substring because it's not in the same order. Right? Is that clear what a substring is? Okay, so now to wake you all up, question. For a string with n characters, how many substrings does it have? I should say that the empty string is also a substring, just like the empty set is a subset. And the full string is also a substring, just like the full set is a subset, right? Okay, so how many substrings does it have? The red option is n factorial, blue option is 2 to the n, the green option is 2 times n. I'll give you a few minutes to think about it. So how many substrings does a string with n characters have? Discrete math question. Okay, so how many substrings are there? See, now there's a lot more variation in the answers, right? Okay. So what's the answer, right? Clearly the majority, it's people agree that it's not 2 times n, seemingly, which is right. It's not 2 times n. So it's between n factorial and 2 to the n. Discrete math question. Yeah, okay, so what did you say?
I said 2 to the n.
Why?
It's a very like mathy answer. I don't know. I just think of it as like if you put like the binary number underneath all the characters,
Okay,
with 0 means it's included in the substring, or 1 mean it is included in the substring,
okay.
it will always be in the same order. And so for you to figure out how many numbers you can make with that binary number on the substring.
Okay, so okay, that's one argument. Yeah.
I also think it's 2 to the n because if you put n equals 2, there would be the full string, the empty string, first character and the second character, so that's 4. 2 to the second power is 4, and 2 factorial is 2. So it's split.
It could also be 2 times n, though.
Yeah, but that's obviously not it.
Why not? Tiny. Who thought it was n factorial? I mean, raise your hand. Does someone want to tell me why they think it's n factorial? Yeah, go ahead. Okay. But that probably happens with 2 to the n as well, because 2 to the 0 is 1. Yeah? Back.
It's the difference between substrings and permutations. So like power set is just 2 to the n.
Okay, power set is 2 to the n. Someone had their hand up somewhere over there. Okay, so yeah, well, the answer is 2 to the n. It's not n factorial, but I deliberately had n factorial as an option because that usually confuses people. So why is it 2 to the n? Yeah?
If you just use 0, like an empty subset, 2 to the n is the only one that works.
Sure, right. So one is you can eliminate things by just, which is clever, right? You just use a simple choice, you work it out, and you say it must be one of these or the other. But in terms of maybe a more mathematical proof as to why it's 2 to the n, so one is like this binary string argument, which is a valid argument. Another way to think about it, which is equivalent to the binary string argument, is so when you have a string with n characters, for each character, which is exactly the same, I guess it is the binary argument, you have a choice. Is it in the substring or is it not? Right? So for every character, there are 2 choices. Let's assume all the characters are distinct. Let's make life easy. If they're not distinct, then things become complicated. I should have said they're all distinct, but I shouldn't say that. And distinct. Okay. So for each character, it's like it's like sort of a yes or no, right? Which you can also think of as a 1 and a 0. And you have this choice for every character. So it's 2 choices for the first character, times 2 for the second, times 2 for the next, so on and so forth, which gives you 2 to the n. Right? 2 choices for each character. Does that make sense? It's not permutations, right? Because you're fixing the order, yeah?
Wouldn't it still work for non-distinct since it would just be treated as a different one of those to still include?
You have to be careful because then, okay, so if you took AAB, right? When you pick these 2 and you pick these 2, they're actually the same substring, right? So actually in this case, I think you get maybe only get you get 6. So when it's actually when the repeated characters, then the formula is more complicated. It depends on how many repetitions there are. Yeah. Okay. So this is the problem. Okay. So we know that there are 2 to the n substrings. So now let's write a piece of code, recursive, to print all of them. And then we'll do it with a stack. So what you'll see is that something that sort of really obviously needs recursion can actually, you can remove the recursion by using a stack. Okay, so I'll leave this here. So I want to write this function I'll call void print all substrings of some string s. Okay? This is a bit tricky. It's not that obvious how you would do it. So I'm going to pause for a bit, think about it. So what's the approach? What's the approach? Anyone have an approach? Yeah, you have your hand up? Sort of, kind of. Sure, but more detail. Like, so how are you going to set this problem up, right? So you need to write a piece of code that's going to generate all the substrings. It's kind of similar to generating all permutations. Yeah.
You would start by printing just the first character.
Okay. Yeah.
I think it would be good to start with like the base cases for recursion.
Okay.
You could monitor the length of the substring, then when it gets to the same length as the string, terminate, or like you would terminate.
Right, so there is something about terminating when you reach everything. You want to make another go at it, yeah. Okay, you're going to need more than one call. So you're making it recursive. Okay, good. Okay. The whole string is also a substring. That's the way you get to the end, right?
Then get to like kind of like ABC, BCD, and then kind of like go off until you have something like A.
So I want to know, okay, so let's just say, suppose we're doing recursion, right? One of the things you need to figure out for any recursive function is how many arguments are going to be in that recursive function. What are the arguments? So someone had their hand up in the back, yeah. Sure, right. I mean, yes, what the arguments are. Not instead of how many you write, like what are the arguments? But what is the approach? Like if I put you, by the way, a friend of mine who had interviewed a while back, like he had to print all permutations. Like that was one of the questions that he got, and I think it was Google or something. But so this question does come up, yes? Good. Good. So right. Good. So this is the way now we start thinking recursively, right? You say, look, this picture says for the first character you make a choice. Is it in or is it out? You get all the substrings from what remains, and then you choose to attach it or not. Right? That's the good. So I think when you have that idea, you can start pushing that into, we can start converting that into code, yeah. You need two indices as arguments. Why? You could imagine the endpoint being fixed and one of them is just marching down. So you could do one. Okay, so let's take this idea further, right? So this idea was using recursion. I'm going to be a little, well, okay, so let me, so sort of, I'm going to write two steps. Take away S0, which is the first character of the string, right? So you have the first character of the string. Take it away. Then you can say recursively generate all substrings of S going from 1. I'm just going to assume that the length of the string is n, just to keep it simple. So n is the length of the string. Recursively generate all substrings. Like recursively generate and I guess and print them. Then, or technically I should say append S0 to each substring. So append to the beginning. Of each to each substring. And and then print. Yeah, does this make sense? Yes?
Could you have recursive call where you have the current permutation you're working on?
There's no permutation, substring.
Of current substring you're working on, the original string, and then just count it down like binary numbers from like 1, 1, 1, 1, 1, count down to 0, 0, 0, 0, 0.
Yes. So we'll get there. That's so. But does this logic make sense? Yeah. It is. It is. Yes. The original string is a substring of itself. The empty string is a substring of itself. Is a substring as well. Does this logic make sense? Right? So you first imagine that you remove this character, recursively generate everything that's left, all the substrings of what's left. Then for every substring that you got by looking at S from 1 to n minus 1, you take that substring, you append S0 to the beginning of it. Now the question people have, but how do you know this is going to work? How is it recursively going to work? But that's like the magic of recursion, right? That's when you start thinking in this way, it's extremely powerful because it now gives you this tool to solve problems almost like, it's almost magical, right? Because you say that you just recursively figure it out. More mathematically, the point is if you can go from the solution of a sub-problem to a slightly bigger problem, then essentially you can stitch it all together to get a full solution. That's the more mathematical reason for why recursion works. But does this logic make sense? Okay. Now, the minor problem with this approach of doing things is you're going to have to store all of these substrings, right? And let's just say that I don't want to generate all that memory. Because as we said, there are 2 to the n strings, and I don't want to generate all the memory for storing all of them. I just want to print them out as soon as I see them. Does that make sense? Yeah? Loop through all of these? Yeah, but then you have to append it to each substring that you generated. This appending means that you need to know what all the substrings are. Does that make sense? Yeah?
Did you pass it like as a
Okay, good. Yeah, pass what?
the substring to the next one and like append it as you print?
So let me say this in a different way, right? So you have like steps 2 and 3, right? Can you somehow convert each into a function call, a recursive call? So step 3 is going to be step 2. Step 2 is obviously a recursive call. Can you make step 3 also into a recursive call to a function? So I have to now generalize your function a bit, yeah?
I'm not sure if this is the same thing, but you could pass an S0
Okay.
into the child process,
Hmm.
and then print both at the same time. Print the one without and with.
So note that this recursive function seems to be doing something very similar to this, meaning that it's generating all the substrings here. In the second call, you don't append anything to the beginning. And in step 3, you actually append S0. Am I making sense here? Yeah. Exactly, exactly. But instead of actually returning the substring, I'm going to think the opposite. I'm going to pass S0 down. You'll see. So yes, the idea is, the logic is, once you have a substring, you kind of, one way to think of it is return it to higher levels so that those higher levels can append other characters to generate more substrings. The other thing is we can pass S0 to the, so there are going to be two calls. One call is going to get a first argument of nothing and a second argument of the remaining string. The second call is going to get the first argument S0 and the remaining call is just, the remaining argument is this string. Does this make sense? Sorry, 1 second. So let me finish up here. Is this starting to make some sense? We're going to have to do this with a stack, so we're going to make things even more complicated. But first we'll understand the recursion, and then we'll see. Yes?
So what do we do when there's only one character?
Where?
Where? I mean, eventually you're going to cut all the characters.
Good. Yes, you're going to take each character, and just as this approach says,
Where does that leave us?
where does that leave you? Two words. Base case, exactly. Leaves you the base case. Yeah?
Why can't these two recursive functions be combined? Like, why can't we pass S0 into the one that generates all the substrings and then just print twice in that same function?
You're going to have to print twice, but then eventually print 4 times and 8 times. Like, you're going to see that you'll see the answer as soon as we start doing this. Yeah.
Does that mean that the empty string has to be handled separately from recursion? Because otherwise you can have empty strings?
No. We'll see that actually the empty string and the full string, all of it will be generated seamlessly with what we're doing. You see, the thing is, this step 2 and step 3 are exactly making the yes and no choice for the first character. The first one is actually the no, and the second one is the yes. Does that make sense? So the way to think about this process, yeah.
So the first part is the no. You're not including the first one, but you're taking everything out and taking.
Well, you're just generating all substrings recursively.
And the second one is just adding the first, right? Just the yes.
It's the yes with all possibilities of the second part. This is another way to see the 2 to the n. Because it says that whatever substring you get from the latter portion, each substring there generates 2 substrings of the whole thing itself and one with S0 appended. Okay? Am I making sense here? It's finding a little hard to read you, which means that you don't understand what's going on. Usually when you understand, yeah. Hopefully, yeah. Hopefully the rainbows will start coming and the unicorns will jump or whatever. Or you'll just be in like deeper and deeper fog, right? Until at some point you're at the stage where you don't even know what question to ask. Right? Yeah.
So we do the entire recursive process twice per call rather than storing it and.
Exactly. You make 2 recursive calls. In the end, the code is going to be like 6 lines. Okay? That's it. It's going to be very short. Okay, so, but very carefully chosen. So, do you see the first level picture? Right? So, you're either choosing it or you're not. Right? And then you make a recursive call here. Now, I want you to think about, so this is what it was at the beginning. What is it going to look like at some intermediate stage of this process? Because that's the way that you'll actually figure out how to write the code. Now that you know what to do initially, you have some picture, however hazy, what's it going to look like at some intermediate process of this stage? Does this make sense? So there's one call being made here. This is another call. That is going to make its own 2 calls. This step is going to make its own 2 calls, so on and so forth. So at some process like as you're going down, I don't know if I'm explaining this right. Right, so you pass S0 onwards, but then it seems like you're going to be passing more stuff as you go down. I want to know what it looks like at some intermediate stage, yeah? Okay, good. Okay, good. So, okay, I mean, some meaning is emerging from the fog here, right? So what's happening is, if you think about it, this is the problem about teaching this, right? It's so clear in my head, I cannot imagine what is confusing, right? But it's because it's not that I've suffered through the confusion, but it was 20 years ago, so I don't remember what it's like to be confused. That's why usually when I ask one of these questions with like 3 options, I just let you talk amongst yourselves. Because you're a better teacher to your friends than I am. Because you're at that same stage where like it's like you got it, now you know what the confusion is. And here I'm like, what is the question? Like, it's so obvious. There's those 2 recursive calls. What else do you do? But okay, right. So good. So, but the reason I'm walking through this process slowly is to show you the process of thinking. Right? This is important, right? So this is how you think about these problems. If I give you the solution, you look at the solution like, oh, I gave you the solution. This looks good. I make sense. And then but how do you come up with the solution yourself? So you kind of start by making these approaches, realizing there are problems, and then fixing them. And then, so again, start with like, what is the first thing you're going to do? Once you have some clarity on that, then you start thinking about, if I reach an intermediate stage of the process, what do things look like? And then you'll see the recursive function will write itself. So good. So what was said was, look, so the first call, so I'm just going to imagine doing it this way, right? This was the initial string. In the first call, what you have is this. I'm going to leave it like blank to say that this is not going to be part of the substring. And then you're recursively working with what's here. But in this part over here, what you've done is you've actually chosen that. So I'm just shading it to saying that S0 has been chosen. And then you recursively work on what's left here. Does this make sense? So you have not chosen, so S0 is not in the substring. S0 is in the substring. Okay, what's going to happen at this stage? I'll pause. I want you to draw it out. I'll give you a few minutes. You can talk, do whatever. But I want you to draw out what the picture looks like for these 2 things. Am I making sense here? Does this picture make sense? There's this dashed part is what you're still going to process. And the shaded and the solid part are what's been chosen. Yeah, someone had their hand up. The visual, yeah. Yeah, you have to, yeah, exactly. I've forgotten this. Like for me, how many of you have seen The Matrix, the movie? Right, that's what it's like to me, right? I just see code and it all makes sense, right? I don't need pictures. But those who are not the one, they need the way of converting to visuals. Yeah, go ahead. All right, so draw the pictures. Question, yeah?
For this picture, we're just doing the first recursive call, right?
The first recursive call from, well, this is, I guess, the second level of recursive calls. This is the first level.
We have 2 recursive like functions, and this one is just the first.
Yes.
And then
No. So there's only one recursive function, just called twice. It's called twice with differing arguments. So hang on a second. Let me. Yeah, question? When does what? Well, yeah. Yeah. Well, you'll see. Yeah. Okay. Do you have some idea of what the pictures look like? Right. So what does this picture look like? What should I? Yeah. Okay. Good. And the rest has to still be processed, right? So S0, S1, not present. What about this? S1 should be, S0 is not present, but S1 is there. And then in this picture, you have this. This is not present. And here, both of these are present. Yeah?
Are we assuming for like the bottom right case, if we're there but we haven't processed the code yet, that the first character S0 has been printed and we're like printing in front of it, like in the same line?
No, so what you would do is instead of printing it, you would store it. This is exactly the recursion will do it. Like it will store it in this auxiliary string, and finally when it hits the base case, it prints that auxiliary string. It prints exactly, right. Yeah?
Could memoization of some sort like speed this up, or would it not?
Yeah, this is pretty much the most memoized way that you would do it. I mean, what I'm going to write is, again, it's going to be like 6 or 7 lines of code, so there's not much more that you can do on top of it, yes?
So just to clarify, between each level, so from the first level to the second level?
No, you're going to print at the leaves. Huh? Printing, sorry, then.
Just to clarify, so like step 1, you said would take away S0 in that first level, and so in the next level you would be repeating step 1 but with S1 instead.
Exactly, precisely. So the only difference between all the levels is that instead of 0, there's another index I. So they're basically tracking an index, right? So each level is given by an index. But note that the different calls at each level are like having all kinds of patterns amongst the first 2 characters. Next level, you'll have all patterns amongst the first 3, first 4, so on and so forth, until finally when you reach the leaves, you basically have all substrings. So if you go all the way down to the left, you get the empty string. If you go all the way down to the right, you get the full string. Beautiful, right? So you get everything. And this is equivalent to generating all binary strings. It's the same picture. Yes? Sorry, I can't hear you. You mean one more level? Or with an actual string? With an actual string. So let's say you have A, B, C, D, right? So what you have A, B, C, D. And so you already have A, B, C, D. So A, B are actually in some sense not chosen. You have C, D. A, B, C, D, B, C, D, and A, B, C, D. So the way to think about it is in all of these substrings here, A and B will not be present. In this, it's going to look like A is not present, B is present, and then some substring of what's left. In these calls over here, no, I'm sorry, no, this is correct. A is present, B is not, sorry, let me redraw my pictures. In the substrings here, AB is not present. In the substrings here, B is present. Here, A is present. And here, AB is present. That make sense? Right, so you have all these possible patterns. Okay, so now what we start getting at is essentially the right recursive procedure is going to have 2 arguments. One argument for the portion on the left that has been fixed, one argument for the portion on the right that has not been fixed. There are other ways of thinking about it. You can also have the right portion be represented by an index, but let's just use a string. Someone had their hand up. Okay. let me keep this picture here. Yes?
Wait, could you just like change the function from a void to a string, and then when you print, you just concat the first bit as 0?
If you start returning values, the problem is that you'll see that you'll have to essentially what happens is that's closer to what this process is, where you're going to have to store all the strings that have been, like, if you think about what happens in this process, this call is going to need access to all the strings that get printed here. So then the returns like is too much, right? So you have to you can do it that way. You'd have to store it in a list then. And
For the bottom four boxes for the second one, yeah, that one. How is the view why is that one passing?
because what you'll see is that once you've chosen something to be in the substring, you'll always pass that down. Like that choice gets fixed. Okay, so now let me write the recursive code, and then it's going to hopefully start making sense. Actually, no, let's take a break for 5 minutes, right? And then I'll write. So take a break for like 2 or 3 minutes. All right, let's go back. So, interestingly, we wouldn't need any of these lectures if all of you were taught Haskell to start with. There's a school of thought that we shouldn't teach any of you Python or anything. We start with Haskell. Haskell is it's a functional programming language, so you can only do iteration. Only do recursion. There's no iteration. There's no for loops. All you can do is recursion. So every single thing has to be done through recursion. So I would recommend highly doing a course in functional programming, because I think it makes a lot of these concepts really clear. But I wasn't taught that way either. We were taught C, and I also struggled with recursion. Okay, so now let's go ahead and let's write the code. So void print all substring. We will have two arguments. One argument for this portion and one argument for the latter portion. So I'm going to give these two names. I'm going to say the first argument is what I will call is the fixed string. The second argument is the remain string. It's like what's fixed and what remains. So in what remains, we make choices. And in what's fixed, we don't make choices. So let's start with the base case. Okay? So if, now I'm going to give you a bunch of options here, and you tell me which is the right option. What is the base case? Like this is when it's going to terminate. So is it, I'll just write this sort of in Python-ish language. The length, the red option is the length of the fixed string is 0. Is it the length of the remaining string is 0? Or is it length of the remaining string is equal to n? Remember, n is the length of the original string. So, okay, I'll give you a minute or two. What is the base case here? Tell me what is the base case, right? Give you a minute to think about it. Okay, so what is the answer? The answer? Blue, that's right. So when the remaining string is 0, then we have the base case. So if the length of the remaining string is 0, then what do you print? What should you print? The fixed string, right? So you print the fixed string and then return. Right? So this is the picture that we have here. This is the fixed string. Where, there's some subset of this that has been chosen, and this is the remaining string. Now what we'll do with the remaining string is we pick out the first character of the remaining string and then decide, do we put it in or not. So I'm going to write this out sort of in English, but essentially, you can pick it out. So this would be, well, I can just write it out. So this would be the remaining string 0. This is the 0th character of what remains, right? And then what we do is we're going to add it to the fixed string and not add it to the fixed string. So, and then I'll say string the new remaining string. This is equal to, okay, so there are many ways of doing this. You can also do a pop operation on the string, but essentially I'm going to write it out over here in, it's the remain string, it's the remaining string without the first character, without this character. Does that make sense? This is the new remaining string. And unfortunately, I've done my indices in a particular way. Actually, if you think about it, if you switch your indices, some of these things become easier. But there's also a pop operation on a string where you can just remove the first character, right? So this is the remain string without the first character. Now we just make two recursive calls. So we print all substrings. What we're going to do is we'll keep the fixed string as it is, and then we do it with the new remaining string. And then we'll make a second recursive call, print all substrings, where we do the fixed string plus C. So I'm appending this character to the end. That's what I mean by plus C. And again, you can use an append, you can use any operation, and then you have new remaining string here. And that's it. That's the entirety of the function, right? So it's, okay, maybe there's more. 1, 2, 3, 4, 5, 6, 7 lines. And then, of course, we have to make, for calling it on any string, so just to complete this picture, print all substrings. If you want to print it on some string S, and this is like, we just make a single recursive call, so we'll do print all. I'm sort of doing the overloading over here. So your fixed string is just the empty string. This is empty, right? It's not a space over there. It's that, right? It's the empty string in S, right? Because the initial fixed string is just empty, and then you're passing the string S. And so you'll observe that if you always follow the first recursive call, you end up at the empty string. If you always follow the second recursive call, you end up at the full string, just as our picture here is shown. So this is the recursive code. Okay? Does that make sense? Questions?
How do you handle the case where the substrings are the same?
What do you mean?
Earlier on the previous question, you were saying if you had AA, B.
I'm assuming non-distinct. Good point. I'm assuming non-distinct here. But that's a.
Are we assuming distinct here?
I'm sorry. I'm assuming distinct. All distinct characters. Sorry. So assuming all distinct characters. It's an interesting challenge to do it if you don't assume they're all distinct. What you can do is you kind of find out the portion over there which all have the same character, and then you decide to put 0, 1, 2, 3, how many ever there are. So you iterate over them. So you have to put your recursive calls in a for loop then. Okay? So that's why the test questions are going to be variations of this, where I'm assuming all the characters are distinct. Okay? Okay, so this, I have given the code for this. I've shared a box with you which has this code. But that was not the point of the lecture. The point of the lecture was to do it through stacks. But you'll see that it's not too hard. Once you have this logic down, it's not that hard. Because we know what the arguments are, we know how to manipulate the arguments, and we know what the recursive calls are. So we can simulate this entire process through a stack where the elements of the stack are going to be pairs of strings, and you'll pop and you'll push in two pairs which have this. So let me write out the code for that now. Any questions about the code here? So I'll keep this picture over here. Yes. Oh, yes. There. Yes. Okay. Yes, in the back. Why do we call this function or this one? This is just so that, so technically this is where all the work is happening, but suppose you wanted a function that just printed all substrings of a given string. You need to be able to call this with the right arguments. So I'm just telling you what are the right arguments to call it by. Right? So this is usually, you'll see this in recursion, that you have some additional arguments that are required for the recursion, and then you'll have a wrapper function that sort of calls it with the right arguments. Yeah?
So like C++ doesn't have default parameters, like you can't have an automatic value.
I don't think you can have, I don't know. I mean, C++ keeps changing on me, but you can have automatic, I guess. But there's a difference here, right? This has two arguments, this has one. So, yes? Over here? Because remember, over here you're making a choice. Do you add B or not? And that's what's happening here. So think of this character here is actually B here. Right? So you're making a choice. I do not add B, that's the fixed string, keep it as it is, or I add, I'm sorry, B is the character C, but I add it over here. Okay? Yeah.
This way, or is it? Because I feel like it'd be the same if you just switch the logic, so it's the 1 plus C first and the.
Good. So you can reverse these, and it will be exactly the same, except the order of printing would be different. The first string that gets printed is the full string, and the other one is the empty string. So this only, changing these will only change the order of printing, not the actual output. Or rather, it's correct in both cases. Okay. All right. So again, what I want you to do is, I know this takes some time to understand it. Once you get it, look at my code where I've implemented it. You can just check it, then try to write it yourself. Okay? Now, how do we do this with stacks? Again, if you think about what we did at the beginning, it's not that difficult. You basically just push these. You have stacks of pairs of strings. So I'm just going to create a class that I'll call pair. I'll have two strings here. So the first string I'll call fixed string, and the second string is I'll call remain string. Okay? And now let me write out this function over here. So let me just make sure that I have my notes on me correctly. Okay, so I'm going to write. So I'm going to replace this logic, print all substrings of a string S. So I'm going to start with a stack of pairs. Yes. Maybe I'm getting my C++ notation wrong, but basically what this is saying is this is a stack of pairs. Look at my code for the correct syntax, but I think this should be correct. So it's a stack of pairs. Does that make sense? Okay, so I'm going to create a couple of pairs that I'm just going to call the top and the initial part of the string. So what is the initial? That's like the first thing that you push on the stack, which is the root call. Okay, so I'm going to be a little casual with my notation over here, but you can think of so maybe there's like a constructor here with string S1 string S2 such that fixed string is equal to S1 and the remaining string is equal to S2. Right? So I'm going to have a constructor here where I create a pair of the empty string and S. So this is exactly mimicking the first call that is made. That is what you push onto the stack at the beginning. Then I'll push this onto the stack. So I'm pushing the initial call onto the stack. And then I say while S is not empty, I'll pop the top of the stack. Right? So I'm doing the same sort of idea of recursion. Remember, if you remember this picture that we had over here, where I'm pushing pairs onto the stack, I would pop it and then I would push things into it. So I pop the top of the stack. So I'll say if the top dot, now I have to do the base case. If this is the empty string, then I print the fixed string. Right? This is just the base case here. That's the base case. And otherwise, I do these manipulations, and I would push to. I'm sorry? Yes, I'm sorry. Top dot fixed string. Thank you. Good. So then I can repeat these. I would say the character C is equal to top dot remain string 0. Right? So I get that character here. Then I would say string new remain string is equal to top dot remain string without the first character. Oh, I was hoping to get this all on a page, but I think I'm going to have to zoom out a bit. Right? So I'm just mimicking this process, and then I would push two things onto the stack. So what would I push onto the stack? So I would do s dot push. So first I create a pair where I have the fixed string. So I'll have top dot fixed string and the new remain string. Okay, so sorry, I should have done this in the opposite order, although it doesn't make a difference. Like the output is going to be the same, but it's top dot fixed string plus C, and then the new remaining string. Okay, and then that ends the entire process. That's going to end everything. So sorry, technically I should have flipped these lines because I have to push it in the opposite order, but the output is going to be the same. Yeah.
Is it fine that C and new remain string are being declared in the while, or do they have to be outside? Or is that fine?
This should be fine, because it's going to create that local copy over here, and then once I think it's a character, it'll just get appended, so it should be fine. I don't think there are any. Even you're worried that like the thing might get deallocated or something. I think it should be fine, but at least the code that I've shared with you will do it correctly. I think this should be fine. Yeah? Good. If, yeah, this is what happens when I write things. I should do a continue. Right, so I just go back to the, yeah.
This is clear to me, but some other people might. The stack and the string are named the same thing. So
Oh my goodness. Oh, that is awful. That is awful. Oh no, that oh my god, that's terrible. That's what happens when I write code all of a sudden. Yes, no, that's actually awful. Oh my goodness. I'll change this to str, and I think that should be enough. Yeah, no, it's only needed to initialize the stack. Oh, thank you. That is very confusing. No, sorry, mea culpa. So the string is only used to initialize the stack, and then after that, the stack processes everything. Okay, so this is a fair bit of logic to understand. Ideally, I would have liked to spend more time on this, but I think it's important that you get the recursive logic correct, because only then can you understand the stack-based logic. But once you really get this, you realize that the stack, it's almost syntactic. Okay? So test 2 and homework 2 are about these processes. So what I will give you is a series of recursive functions to do on strings. So this is one recursive function, but there are other recursive functions that I've come up with. And I want you to write them with recursion. The point of the test is going to be do it with a stack. Now the point is, if you think about this process, and going back to our process, where do I have this? There's some notion of backtracking of the recursive calls. And so stacks can be used to simulate backtracking, because this process of recursion is basically like backtracking. Like you go through the calls and you keep going back up, right? And so homework 2 is really about backtracking and stacks. But anyway, so before you get overwhelmed, I want to tell you step by step what you need to do. Print all substrings. Make sure you understand it. Write this code yourself. Then do it with a stack by yourself. I have provided both of these codes in a Codio box. Then I have 3 or 4 other questions regarding the same sort of setting, where there is a recursive function that you need to implement using a stack. The way to do it is first do it using recursion, understand what the arguments are and what the recursive calls are. Once you see like essentially this part and this part, then the rest of it becomes fairly clear, right? Because the initialization is related to sort of like the dummy call. The manipulation of the stack is related to the manipulation of the arguments. And finally, what you push onto the stack is related to the recursive calls, right? Okay, so we're done now. 2 weeks.